Hi guys, let me introduce you to a nice model that tries to look at how class size may affect students' academic performance. So I'm going to use a database from a very famous book by James Stock and Mark Watson called Introduction to Econometrics. We'll find the data in GRETL. So fire up GRETL, and there we are. So let's go and look for the data. So go to File, Open Data, Sample Finds, and you should find the Stock and Watson book here, and we're going to CA Schools database. If you don't have Stock and Watson, you can get this by clicking on this icon here, look on server, and you'll find very many famous textbooks, and the one that you want is Stock and Watson. So install that, and once it's installed, it will take about a couple of minutes. So close down your program and get back in again. So there we are, Stock and Watson, CA School, CA for California. So we have 13 variables here, and what we are going to be interested in is how do we measure class size. So class size is going to be measured by this variable called STR, students teacher ratio, and students performance will be measured by the variable test score. So from the offset, it's really good to get the basic statistics and also to see the histograms. Let's look at test score. So right click, get the frequency distribution, say OK, and there is the test score. So roughly the mean is about 650, and standard deviation would be around 20. Same thing for STR. Right click, do frequency distribution, say OK, and there's your histogram. The mean is about 20 students per classroom, plus or minus, perhaps 2 students. Of course, you can get the statistics, exact statistics, by using your control button, select both variables, right click, say summary statistics, and you can say show the main statistics, OK, and there we have it, the mean and the standard deviation. Let's write that down here. So what do you think the relationship is between class size and student performance? If you think about it, it would be reasonable to think that the larger the class size, the worse the student's performance. So the relationship should be negative. We can find the correlation coefficient by selecting again both variables using the control button or the command button if you're using Apple. Right click and say correlation matrix. So we get a correlation of minus 0.23. Let's put that down here. So we can do better. We can try to run a regression. Or first of all, let's get a scatter plot. There's the scatter plot. So we have students teacher ratio on the x-axis and test score on the right axis. Each point corresponds to one school. The data comprises of 420 schools. I may write that n is equal to 420. Now you can imagine it's very difficult to see what the relationship is from the scatter plot. How do we draw the line? Like this, like this? So to find the line, we can ask GRETL, select the 2 variables using the control button, right click, say XY scatter plot, leave STR on the x-axis, say OK, and there you have a nice regression line, OLS line, and the equation is right up there. Let's write it down. Test score is equal to 699 minus 2.28 STR. To get more details of the regression, we can easily go to Model, OLS. The dependent variable is test score. The independent variable is students teacher ratio. Say OK, there is the OLS result. So we can add in here the standard errors. So the standard error of the constant is 9.47, and the standard error for students teacher ratio is 0.48. We would like to put a hat here, and there is our first regression model. Call this model 1, as it says here in GRETL. So as usual, whenever we have run the model, we would like to do a quick test to see whether class size affects the test score. We want to see what beta says. Check SSS for beta. So we're going to check the sign, the significance, and the size. So sign is negative, as we expected from theory. It is statistically significant because the t ratio here, which is minus 4.75, is larger than 2 in absolute terms, so it is statistically significant. And the size is interesting. 2.28 means that when class size, or when the student-teacher ratio goes down by 1 student, the test score will go up by 2.28 on average. So keep that in mind. So are you happy with the results? SSS. This is what we call a simple regression, meaning that we have one explanatory variable, but usually this would suffer from a number of problems. More specifically, what we call omitted variable bias. So there is another variable which definitely we have to put into this model. Simple regression may be too simple. So let's try to add in another variable into the model. The other variable that I would want to put in is variable number 11, which is called the percentage of English learners. So clicking on this tells you, for example, the first school, the percentage is 0, meaning everybody at this school is good at English. They do not have to go and take extra English lessons. The third school, however, has 30% English learners, so there are many students that are not very good at English and may have to take extra classes. So let's put this into the regression. So what we're going to do is OLS, the dependent variable is test score as before. We can set it as the default. So we have STR, and we're going to add one more, which is the percentage of English learners. Say OK, and there is our regression result. Let's write this down. Test score is equal to 686 minus 1.1 STR and minus 0.65 ELPCT. We can put the standard errors at the bottom as usual. I'll leave the standard error for alpha. So 0.38 and 0.04. Put the hat always, and we can call this model 2, which is what we call a multiple regression as opposed to a simple regression, because now we have 2 explanatory variables. But let's not get distracted with English. Let's concentrate on our beta 1, our variable, because our research question is to know whether class size is related to students' performance. So what we find is, let's do our test again. So let's check for our beta 1 this time, which is this one. Let's check SSS. Let's check the sign, the significance, and the size. So sign is negative, so that sounds okay. Is it significant? So 1.1 divided by 0.38 gives us the test statistic of 2.89, which is bigger than 2, so it is statistically significant. The size, however, is interesting. It's only 1.1, meaning that if class sizes are reduced by 1 student, the average test score will go up by 1.1. This is different from what we got previously. So if you compare the two models, model 1 and model 2, you'll find that they give us very different results. With model 1, the benefit of reducing a class size is 2.28. But with model 2, it's only 1.1. So which model do you believe in, 1 or 2? And the answer is, we believe in 2. This model, because with model 1, we are missing a very important variable, what we call a confounder. So that means we have a variable, what we call sometimes called a third variable, let's call it Z, which affects both the test score and the student-teacher ratio. which could be actually driving the relationship between test score and STR. So in a what we call a Ballantines diagram, we can say this is test score and this is STR. So beta is captured by this area between test score and STR. And this other model, there is English. So we have test score, we have STR, and we have another variable which is ELPCT. So our beta now is captured by this area, which is smaller than the previous one. Some of the variation of test score explained by STR, which is captured by this area, is actually explained by the English. So the yellow area here. So we say that the model 1 is suffering from confounding variable, but when we put it in the model here, it becomes a control variable, which makes the coefficient on STR behave. That's it for now. Thanks, guys.